Welcome to the debate. Today, we're diving deep into a technical analysis of TIR-Judge, which is a pretty novel framework that uses tool-integrated reinforcement learning to really revolutionize how we train large language model judges.
It really is a critical milestone. I mean, TIR-Judge successfully addresses some of these persistent limitations of the intrinsic text-based LLM judges by integrating precise, verifiable code execution. And we absolutely need that verifiability.
Absolutely. So I think the central question for us today is whether this optimization approach, tightly coupling this multi-step reasoning with tool use through end-to-end RL, is actually a sufficient, scalable, and robust foundation for LLM evaluation. Or does its neural architecture just inherently retain these fundamental flaws that mean we have to ground it in something like ontologies and knowledge graphs?
And that's where I land. I believe the performance ceiling for these purely neural judges is structural, even with the tool integration. While the empirical gains are, well, they're stunning, the inherited flaws in explainability, consistency, and maintenance demand that we ground the whole evaluation process in declarative knowledge bases.
See, and I'm going to champion the success of the TIR-Judge methodology as the scalable answer. I mean, the results demonstrate that RL is the paradigm shift we've needed. It's enabling these smaller, more parameter-efficient models, we're talking 8B parameter judges, to surpass significantly larger 32B text-only models just by mastering that really difficult strategic question of when and how to call on external code. That efficiency gain is a massive breakthrough. The real power of TIR-Judge, I think, lies in its architectural innovation. This isn't just, let's give a model access to a calculator. It's about incentivizing agentic reasoning in the LLM Judge by tightly coupling the entire multi-turn judgment trajectory. That includes the internal reasoning steps, the RUC, the generated code, the kick, and the tool feedback, the execution output, OK. All of this gets integrated directly into the policy gradient via reinforcement learning.
Okay, I grant you that. I mean, prior attempts that just sort of prompted LLMs with external tool access, they often showed negative gains, right? Because the model didn't truly understand how to generate error-free code, or more importantly, when to interrupt its own reasoning to go verify something. TIR-Judge really confirms that RL is critical to teaching the model that complex strategic tool use.
Exactly, and the proof is right there in the performance metrics. The 8B parameter TIR-Judge surpasses those 32B text-only models on the PPE dataset, and crucially, it reaches 96% of the list-wise performance of behemoths like Claude Opus 4. The key design principles that deliver this success include training across a diversity of tasks, so covering verifiable things like coding and math, but also non-verifiable tasks, and implementing a structured final reward system that just ruthlessly enforces correctness, format compliance, and efficient, error-free tool use within a really strict budget of 3 calls.
That's a compelling argument for maximizing empirical performance on those predefined benchmarks, for sure. But I just don't buy that it resolves the deep-seated issues that these neurally trained judges face when we move them into high-stakes, production environments. The model is still fundamentally a black box. The evaluation logic is ultimately embedded in prompts, in reward functions, and in trillions of opaque parameters. This architecture, I think, introduces a brittleness around 4 specific critical limitations that a declarative knowledge graph system would address directly.
Okay, so let's clarify those. What are the 4 specific challenges you see remaining?
All right, first is explainability. We can meticulously trace the $carc, trajectory, showing the code execution steps. That's great. But we can't declaratively query why the final neural decision, the score or the preference, was actually made. We need a debuggable, rule-based rationale for that. Second, consistency. Judgments are independent episodes. There is no shared semantic mechanism in this neural architecture to detect and resolve contradictions across different related evaluations. For instance, it could score conflicting factual claims as correct in 2 separate prompts.
I see why you emphasize that. But you could argue the RL structure is designed to enforce consistent behavior through its policy objective.
It tries, but it's not guaranteed. Third is maintainability. Scaling the judge to new, specialized domains, say finance or complex medical evaluation, it requires updating hard-coded prompts and expensive model redeployment. It just fundamentally lacks the modularity that declarative knowledge bases offer. And finally, the self-improvement ceiling, the iterative self-bootstrapping mechanism, TR-Judge 0. It can optimize its existing tool use skills, sure, but it can't reason about its own conceptual gaps. It can't propose structural changes, like identifying a need for a totally new kind of tool based on concept coverage. It's confined to optimizing within a fixed design space.
That structural critique brings us right to our first real contention. Is robust judgment achieved through this careful empirical RL optimization, or does it require external factual grounding? I'd maintain that the robustness we need comes from the meticulous RL design. I mean, they use DAPO, which is basically an extremely robust and stable way to handle the messy, noisy feedback you get from running real code. It stops that noisy signal from just crashing the whole training process.
I'll acknowledge the necessity of that stabilization. Code execution is inherently noisy, so that kind of reward engineering is complex, no doubt.
But let's look at why it creates robustness. Consider the final reward structure. The paper shows the reward R is heavily weighted to ensure the judge is highly incentivized not just for correctness, the RC, but also for strictly following the required output format, RF, and using tools without errors, RT. This rigorous design guarantees high-fidelity, verifiable reasoning. It basically forces the model to be a meticulous executor, which is crucial for high-precision tasks like complex instruction following.
That reward system absolutely optimizes for internal compliance and alignment with the provided labels. I agree, but it does not optimize for external, semantic, factual truth or for consistency across different judgments. If a prompt requires complex multi-hop verification or factual checks that aren't tied to a simple calculation tool, the judge still has to rely on its own, potentially error-prone textual inference.
But if the verification is that complex, the policy should, over time, learn to generate the necessary verification code.
It might learn, but it's never guaranteed to be consistent. A knowledge graph, on the other hand, provides that external factual grounding immediately. It allows the judge to verify claims against a structured source like Wikipedia or some internal database.
Sure, but that complexity adds significant external infrastructure and latency, especially when you compare it to the minimal overhead that TIR-Judge reportedly has.
Maybe, but it solves the profound consistency problem that plagues these LLM judges. A KG lets the system detect when response A claims Paris population 2M and response B claims 10M. The KG can then pull up the context, the defined relationship between, say, Paris city proper and Paris metro area, and resolve that ambiguity based on external context, ensuring the two scores are semantically consistent. Optimizing for an error-free code execution in an RL loop, it just can't achieve that level of semantic consistency.
That shifts the debate toward resource allocation, which I think brings us to our second contention, the efficacy of this purely iterative RL versus a transition to declarative self-improvement. The paper shows that iterative RL is surprisingly effective at reducing the reliance on external supervision entirely.
You're talking about TIR-Judge 0 now.
Precisely. The 0 variant, which is trained without any distilled trajectories from larger teacher models, actually matches or even outperforms its distilled counterpart. It does this by leveraging an RS to SFT to RL cycle. For listeners, you can think of this self-bootstrapping as a student who learns by teaching itself. It progressively generates higher quality self-critiques, uses that to refine its foundational knowledge, and then hones its practical skills through trial and error. This scalability and parameter efficiency, getting that performance from an 8B model, is a massive win for the RL approach.
I'm not entirely convinced by that, because iterative RL only improves performance within its fixed structure. It's a powerful optimization, yes, but it doesn't offer any kind of meta-level improvement. True self-improvement, especially for generalization and long-term maintenance, requires treating the evaluation criteria as modular, declarative knowledge.
So how does an ontological facilitate that kind of structural self-improvement?
Well, with an integrated ontology, The evaluation criteria become structured, queryable entities, instead of just logic that's buried in a prompt template. A domain expert could extend the system's capabilities through pure knowledge modeling, defining a new concept, a new relationship, instead of an expensive RL redeployment. But more fundamentally, the system could literally query its own ontology structure and ask, what conceptual entity types lack dedicated tools? Based on usage patterns and knowledge gaps, it could propose missing tool definitions. The neural system can only refine how it uses the tools it has. A declarative system can propose the tools it needs.
But that immediately shifts the bottleneck from training compute, which is getting cheaper all the time, to knowledge engineering overhead, which has historically been far more expensive, slower, and much harder to automate at scale.
Perhaps, but it guarantees structural integrity. Which brings us, I think, to our final contention: the difference between process transparency and truly debuggable provenance.
And I'd argue that for verifiable tasks, TIR-Judge provides excellent transparency through its trajectory logs.
But we have to be very careful to distinguish between transparency and production-ready provenance.
Look at the case study they did, the one counting the letter O. The LLM Judge correctly generates and executes Python code, response.countO, to get the exact counts, 58 and 60. That demonstrates verifiable, precise judgment. The trajectory log, which shows the code and the exact output, is more than enough to debug what the judge did and verify its calculation. That log is the why for any task that involves computation.
The trajectory shows the steps taken, I agree. But a production system, one operating in a regulated or high-stakes environment, it requires tracing the conclusion back to the governing rules themselves. That is the core limitation of a purely neural reward model. Knowledge graphs achieve this kind of debuggable provenance by enabling every single judgment to trace back through declarative SWRL rules.
So what exactly is an SWRL rule doing here?
It's providing the audit trail. So for example, the system doesn't just score a piece of code highly. The output is backed by a declarative rule trace. I preferred response A because the rule correct code implies it passes tests and follows style guide was satisfied. This gives you complete, human-readable, audit-ready provenance about the decision logic that is simply impossible within a purely gradient-optimized neural judge. Not just what happened, but which rule was triggered.
That level of explicit declarative reasoning, it fundamentally changes the architecture. But we have to factor in efficiency. The paper showed that TIR-Judge introduces virtually no additional inference time overhead compared to text-only baselines. The SFT training phase favors shorter, more efficient reasoning trajectories, so we're optimizing performance and retaining speed, which makes it actually deployable.
Speed is irrelevant if the foundation is brittle. If we zoom out, look, TIR-Judge has achieved truly remarkable empirical success by being the first framework to jointly and effectively optimize reasoning and tool use in LLM judges with end-to-end RL. The integration of tool feedback into the policy gradient is a powerful innovation, and the effectiveness of TIR-Judge 0 proves the scalability of the self-bootstrapping approach.
The gains speak for themselves, up to a 7.7% gain on pairwise tasks over strong reasoning-based judges. This demonstrates that for verifiable tasks like math, coding, and precise instruction following, the neural approach, when it's properly reinforced for strategic tool use, is highly effective, parameter efficient, and fast.
And on the other side, I've tried to illuminate the architectural limitations that persist. The black box nature, the inherent lack of semantic consistency across evaluations, and the brittle maintainability of logic embedded in prompt structures. These pose serious long-term scaling challenges for high-stakes domains. The necessity to ground evaluation in declarative knowledge via ontologies and knowledge graphs emerges as a powerful counter-framework. It offers true semantic consistency and rule-based provenance that these neural models just can't intrinsically provide.
Both approaches offer compelling, evidence-based paths forward, and the material is clear that innovation is moving incredibly quickly. The optimal future for LLM evaluation likely involves a strategic trade-off, focusing on optimizing neural performance for speed and breadth or grounding that performance in structured knowledge for depth, rigor, and accountability.
Exactly. The trajectory of this research shows that while capabilities are accelerating, the very next step is figuring out how to make those rapidly evolving capabilities transparent, consistent, and truly scalable across complex real-world domains.